Hello and welcome. Here we are on lecture 14. You can see from the title, inheritance, which we actually used a little bit in the last lecture, and now it's time for me to fully explain what we were doing. So this is yet another Scala concept we're going to learn about in the Scala perspective and then bring it back to how to use it in Chisel. So inheritance, of course, is referring to an object-oriented programming, the ability to have classes that inherit from each other. So of course, as I said, cover it first in Scala, then how to use it with Chisel. And we'll talk about things like type parameterization. Remember how in the last lecture we had that queue that was pretty spiffy, and the only problem was it required you to have like a uint as the data type. Well, what if you don't want a uint? We can cover that. And then I've been kind of giving some project details all week and a few more advice I want to write down, so I wrote those down. Okay, let's go ahead and fire things up. All right, so why use inheritance, right? Well, what helps, right? Remember the whole goal of this course was to make you productive hardware designers, right, using agile methods. And our best way to improve productivity is to avoid writing hardware, right? And the way you can avoid writing hardware is to reuse hardware, right? So the idea is you want to use other people's hardware, you want to make generators you can reuse, other people can reuse, etc. Right? The whole point is to spend less time writing new stuff per component, so that way when you're writing an actual design, you can reuse a lot of stuff, right? You need a RISC-V core, great, grab a RISC-V core. You need a cache, great, grab a cache. You need a network, grab a network and combine them together, right? So to have these usable components, and so inheritance is one way that makes it easier for us to do some amount of reuse, right? And so there's a few different cases comes up in just programming in general as well as in agile hardware design. And so basically, you can think of it as, maybe people don't just want one thing, they want multiple things, right? So you build, let's say, 5 or 10 classes, and then you find yourself in these classes having very similar functionalities, right? And it's like, wait a second, if there's similar functionality across all these classes, whenever you're programming or writing hardware and there's something that's similar, or even worse, if you as a developer are copying and pasting between file A and file B, that should be a red flag to you. That's a sign that it's time to think about how to, refactor things so they can be shared, right? And so object-oriented programming is one way to do that, where you can have a parent class that has the common functionality, and then the child classes can both inherit from there, and they can have that shared stuff there. And let's say, for example, you want this, shared functionality, you want to change only like 5% of it. Great. Inherit from the main thing, and then override the small part you need to override. It's not just for functionality. Other times you want to inherit an interface. See, actually, I did that in the last lecture, and I didn't, told you to kind of ignore it, but we did it, right? We had a case where we had a queue, my queue, right, in the last lecture. I set the bundle for the I/O, and then I made, 6 different versions of that queue, my queue v1, v0, all of those, and they all extended the original my queue. So they all got the I/O bundles, never had to think about that again, right? And they also let us reuse all of our testing infrastructure because that worked on the MyQ interface rather than a specific MyQ v some version number, right? So like I said, inheritance helps in 2 cases, right? Reusing functionality, reusing interfaces. Sometimes you want to do both. Great. And so in this very seen Scala all quarter, Scala has a lot of features, right? It's a very rich language, right? And so as a result, because of the nature of how you want to do this kind of reuse and this kind of inheritance, there's a lot of different inheritance mechanisms. And so we've already seen some, and we'll see even more today. Okay, so first off, we can just do straightforward inheritance of a class, right? So we've gotten really good at defining classes. For example, maybe we want to define a class parent, which takes in a name string, and then when executed, of course, we can create an instance and then ask it to greet. Cool, works great. So now let's say we want to extend that class, right, with inheritance. So we can make a child class, and now we need to say extends, and then the class we're extending. Now, if we're extending a class that takes in arguments, we also need to provide those arguments here too. So for example, let's say I accidentally omitted these. It's going to say, oh wait, I didn't give enough arguments. So yeah, you need to explain, okay, yeah, if I'm doing a child, I need to have the, this form of the arguments going to the parent constructor. One interesting thing about Scala is for things that you want to modify, you need to explicitly say override. So in some languages, you have a case where you override things and it's not obvious to the programmer. Did it begin the original version, the parent version, the child version? Is it overridden or not overridden? In Scala, you must explicitly override. If you don't explicitly override, it's going to tell you, hey, you need to override if you want to override something, you actually do something different. Cool. So yeah, we have our child class. We can go ahead and instantiate it. We notice in the child class speaks Spanish first, of course. So we're going to get a different greeting, right? So notice how we're using this phrase, hola, right? But it's actually calling the greet from the parent class. So in this case, we have both the child and the parent kind of code intermixed execution. So you can imagine, maybe you have some situation where you want to have some shared function. Put that in the parent class. Now, in this case, it's only one child. You can imagine other childs as well. Cool. Questions so far? In what sense? Oh, so you're asking like how convertible are types, maybe is what you're trying to ask, right? Uh, that's a whole book of material in Scala. But the answer is yeah, there is some ability to kind of do this, right? So, for example, if I said this was a parent, I think that's going to be okay. Yeah, because child is an instance of parent, right? So that's okay. Like I said, there's a lot of type theory uh, possible in Scala, which we're going to gloss over in this course. Yes. No. So Scala only has single inheritance. To do multiple inheritance, you use something called a trait, which we'll cover later today. Yeah, so you'll see an example later today. Um, so that was a conventional class. Now, um, you can also do what's called an abstract class. It's actually technically what I used on Wednesday's lecture, right? Where you can define a class. Now, the rules are if you have an abstract class, it's like a virtual class in other languages, you cannot, instantiate it, right? I can't say, new parent abstract or whatever we want to call this, right? It's going to yell at me because, hell yeah, you cannot instantiate an abstract class, right? The rules of an abstract class is it cannot be instantiated. So that's the only way to use it is if you inherit it, right? So in this case, we're going to have, in English that, extends the parent, and we have, our English greeting phrase. We can also have another sibling, another child that does it in Spanish. So this is basically the same thing we just saw in the prior slide, just now we're having it via an abstract class. And so there's different ways that make sense semantically for a project. Sometimes you have a common functionality and you use that, and then you maybe want to extend it in other cases. Great, you can just use a regular class and then extend it. Other times you have things that are arguably all kind of peers. There's no like default or main version, but you do want to share code across them. Perhaps in that case, you should have an abstract class to kind of encapsulate what you believe to be the shared components, and then each of them can independently inherit it. And so it's one of these things where it's not just a simple engineering calculation. It's actually a little bit of code organization and even style about how you choose which of these mechanisms you want to use in which ways. And as asked a second ago, we'll come to traits to do multiple inheritance. But for now, yeah, classes and abstract classes can only do single inheritance. Yes, correct. Yeah, yeah. So I'll repeat the question for the recording. Since it's an abstract class, I didn't need to use override for this. Correct. I believe it's okay if I say that, but it's not required. Um, if I didn't have that, it's going to say, oh, wait, that field is not filled in. So notice how it's a little bit unusual. I'm happy you brought this up. In Scala, right, I've been pushing vowels all quarter. This is a val that's just a type deck. But wait a second. Normally, the whole point of val is you single assignment, it's a reference. And so this is defining there's going to be a val, but the assignment's actually not occurred because it doesn't exist because it's abstract, right? So yeah, and you actually need to have the concrete instantiation here. But yeah, override is not required if you're overriding an abstract class because you need to have that concrete implementation. Now, let's say, for example, I want to do my greet, my own version of greet. I think that actually would be required. If I did greet, uh, you know, alternate, whatever we want to call it, I think this actually would be required because this is a concrete field, right? The reason why this needs to be overridden is because it's abstract, right? It's a type. There's no actual meat there. Um, so I would need to say override def, correct? Um, Alternatively, if I gave this a value, it's going to now tell me I need to override keyword because it's a concrete thing. So because it's really abstract, that's why you need the override Oh, sorry, you don't need to override, but when it is concrete, then you do need to override. Great question. Yes. Yeah, I think we literally can. Let's try it out. Let's say, hey, I want to have a def greet and then leave it like that. So yeah, so this is, you know what? You better give me a same problem, right? Greet is now abstract. So then I need a concrete version in the actual concrete instance. And then in Spanish is the one that's breaking it now. So if I comment it out temporarily, yeah, cool. Um, Not quite templates. I see templates. This is plus, at least for me, a lot of the importance is everyone has their own, take. It's a very complicated concept. It's about ensuring certain things happen at compile time versus runtime. That's kind of a key part of what templates provide. And This is not what this is. Now it's interesting, not covered at all in this course. Scala has macros. So you actually can do certain stuff guaranteed at compile time. You can even have compile time plugins. So actually for Chisel the last 4 or 5 years, it's had a Chisel plugin. So it's not just it's simply a jar, it's like the Chisel package. It's actually the Chisel package and a Chisel plugin. The plugin actually does certain things at compile time guaranteed. But that's a whole other super deep Scala concept thing. But yeah, so the way I think of this stuff is really just doing object-oriented stuff. And if you kind of sit down and think about it, the choices Scala made, a lot of them are pretty defensible. I think the one that's the most conversation worthy is disalign multiple inheritance. Multiple inheritance, it's a well-known challenge, something called the diamond problem, where basically if you allow people to have multiple inheritance, it comes ambiguous situations where you get certain things from if you have too many things you're inheriting from. And so their solution to that is this notion of a trait, which I think is a pretty interesting solution to that. Yeah. How deep does inheritance tree go? Usually not too deep. Today I'm going to show you two inheritance diagrams, and they're not even 5 deep. They're more like 3 or 4 deep. Because yeah, like you mean, this is like a good thing to bring up, right? So when it comes to code, right, we're kind of balancing multiple constraints, right? We have, obviously we have to do the right functionality. I tell you design for reuse, design for performance, etc., but also design for readability. A lot of times, if you have a lot of functionality that comes into your code via inheritance, that can be extremely surprising to people reading your code who are not familiar with your code base, right? Because all of a sudden you like refer to a variable, like where did that variable come from, right? This is one of those times when it's super helpful to have an IDE because you're reading this code, you're like, where does method come from? Where does highlight it, right click, figure out where it came from, right? And so when it comes to some things, yeah, inheritance abuse becomes a little tricky to reason about sometimes. And so I would argue in that same vein, having a super deep inheritance chain, like 10 deep, and you're trying to figure out where a certain method came from, that seems really rough, right? So you sometimes shallower might be more readable, right? Yeah, and that seems tough. I'm not saying it's wrong. I'm just saying it seems tough, right? So hopefully you have an ID to help you make sense of that, right? That's where the IDs can really, earn their keep. Okay. Great. Okay, so class, abstract class. So as promised, actually it is deeper than 5. Here is the Scala type hierarchy, right? Um, so what's interesting about this is we don't see all of these classes, right? In this quarter, I kind of told you, yeah, just use seek. And seek's kind of been our use for everything kind of collection. And some of the stuff we've used in the array buffer, that's a mutable collection. So this is the immutable collection. So that's why you don't see it on this diagram. But you can see there's actually quite a variety of stuff here. And so what's fun is looking at this, it's almost like taxonomy, right? Trying to figure out what are the traits of a certain collection and how do you kind of tease those apart, right? So you may notice, for example, okay, well, so there's a notion of traversable, right? Okay, and then iterable. Okay, these are all iterable collections. The iterable means they have some sort of multiple items. And then, okay, well, how do we go about these items? Well, there's sets, maps, and seeks, right? So seek or sequence is the ones we use most often, right? So sequences have this notion of an order, right? As opposed to a map, which takes in arbitrary keys, right? versus a set which has components that may not necessarily be keyed, right? So you kind of see they're like differentiating by like the way you're using these things. Even within a seek or sequence, right? They actually break it into index seeks versus a linear seek. You're probably saying, what the heck does that mean? Looking at the bottom row makes that more clear. So when we've run the interpreter, you've often noticed that even though we ask for a seek, it gives a concrete class. And the concrete class, depending on what we're doing, is either a list or a vector, right? And now actually we can understand why, right? So a list, it's not stated it's a linked list, but perhaps it's linked list like. That's really great for, in order traversal, right? You can just do next pointers the whole way through it or something. However, if you want to get to index element 4, not easy to do. Then in which case you want more of a vector like an indexable thing where you can say, I want a certain index. So you can imagine a smart compiler looking at how you use that seek in that code scope and say, you know what? If you never do an index lookup based on a number, perhaps I'll give you a list. But if you do an index lookup based on a number, I can give you a vector, right? And so that's the kind of thing you can do. Technically, I believe list is not quite linked list, or maybe it's a fat linked list, however you want to call it in Scala, where it's like 32 elements at a time. It's like 32 elements and then a next pointer or something like that. Because maybe it's only 30 and then a pointer using the last 2 elements, something like that, where basically it's some amount of spatial locality and then a pointer rather than a pointer per element. As a performance person, it makes me happy. Like linked list, 1 element per pointer is, I wish we didn't teach students that. Okay, looking a little more at this diagram, we can still appreciate what's going on in the kind of range of things possible, right? Notice how there's 2 colors. Believe it or not, the blue ones are already abstract classes, right? So these are the ones you can ask for, but the compiler is going to give you a concrete collection. Also notice there's like different thicknesses of lines. The bold lines are the default implementations chosen for concrete classes, right? So for example, if you ask for a seek, it's going to give you a list most of the time. However, as we've experienced, sometimes it gives you a vector, right? And then if you go to this web page, you'll see the dotted line corresponds to if you can convert things rather than actually inheriting. It's a subtle point, but yeah, go ahead. Oh, good question. What's interesting between abstract and generic? So generic means you take a type, and that type is a parameter. So like that's more like the C++ templates you were talking about earlier, where if you have a collection and the type the collection holds is parameterized, in C++, that would be a template typically. In Scala, you have 2 choices, right? You could be obtuse and take advantage of the fact that all objects are objects, inherit from objects. So you can say, oh, you know what? I'm a collection on object, and thus I can take anything inside me. Or that's not always the most efficient or most clear. Scala does have support for generics. You can say, you know what? I have a type parameter, and I want the type parameter to be passed through, and this is the type, and I want to do things with the type intentionally. And so, yeah, so there's a lot of support for really fancy type analysis in Scala, not just matching types. You can say, with regards to inheritance, there's covariant, contravariant. Forgive me for not remembering the difference between the two. Basically, it's describing how which types can be cast to which types and under which conditions. There's all these kinds of bounds you can place on things. There's a whole rich theory to that available in the language, much more than you've probably seen in other languages. But for the most part, for us at the base level, we don't have to worry about this. It's going to be a problem for the chisel developers, or it could be a problem for other people. But for us, we can kind of just enjoy it and not have to worry about it most of the time. Which is why I've been writing Scala now for almost 14 years, something like that. And I learned this and then I've forgotten this, and it's been totally fine. Great. Other questions? It's instantiating a list. The question is, yes, wait, seek is abstract. How come I keep saying things on seek? How is that working out? It's giving you a list. But because it's originally of type seek in the way the code is expressed, you can interact with things that expect you to have a seek. Depending on the Scala style guide you read, some Scala style guides will recommend not using seek because it's abstract, and you should be deliberate, intentional about which data structures you're using to convey to people which performance trade-offs are. Because some of these data structures, you can imagine they have some operations are faster or slower depending on what kind of axes you're doing. I read those style guides, and I've done benchmarking as a performance person. If you have some cases, it does matter, but I found that this kind of using Seek everywhere, may not make those style guide people happy, but I feel like it's actually advisable in many ways because um, for a lot of people, performance differences do not materialize. Uh, Additionally, someone's a common performance programmer, performance optimizer. People, when they think they're doing performance optimizations, often get it wrong. And so that's why I also recommend against premature optimization. But the other thing is typically in actual chisel designs, I would say that I've written like a compiler working in chisel, but actually in the actual chisel design, usually your collections aren't that big, right? You have, 10 modules or, maybe 16 ports or something like that, right? And so they aren't very big. If they're not very big, performance differences are washed away by everything else. And so for simplicity, especially for this course, I just say for immutable, use Seek. For mutable, use array buffer. Technically, if you go digging around, you can get a Seek that's mutable or an immutable array buffer. But I find just by having it in this course, the association that Seek is always immutable and array buffer is always mutable makes it way more clear for everybody involved. Question, yes. That's a great point. So I'll repeat that for the recording. So the point was you're writing things in Chisel, right? It's a Scala program that runs only elaboration time. Um, so as a result, that performance implications for these collections may change your elaboration performance, but it won't change performance in hardware design. Definitely true. Yeah, I mean, software simulation is just one possible output of a hardware design, right? Could also be pushing it through a CAD tool to get a hardware design too, right? Um, cool. But yeah, anyways, here's an example class hierarchy, right? And this is a pretty big one, right? This is, the collection library inside Scala. So a typical project in this course might only have, two levels, maybe three, right? And that's totally fine. Um, okay, so that was a Scala dose. So how do we do that in Chisel, right? Um, so taking a step back, right? I keep saying reuse, reuse, reuse. That's the whole point. So how are we getting reuse, right? So far we've been saying, you know what? Let's build a parameterized generator, right? Take some parameters into class arguments, tailor to the person's needs, boom, return to them. We've seen that both as self-standing modules or even in some cases, not even modules, right? It's just, chisel code coming out with functions like that. We've seen that. Um, we've also seen, defining bundles, and those are kind of handy. Um, Worth noting that when we make our own custom bundles, and as you see down below, we're actually using inheritance, right? So inheritance, we've been using all quarter and we just haven't been thinking about it, right? When we declare a module, we say extends module. That means we're inheriting from Chisel's module. And the things we're inheriting are the stuff that makes Chisel actually work. Same is true for bundle, etc., right? And so when it comes to us designing our library of generators, we're going to make a project. Sometimes you just want a library of generators that each your own independent classes. Great. Sometimes some of those independent generators, we might want a companion object. We've seen those for factory methods. Can do that. But other times, maybe you want to do things via inheritance, right? Um, and so maybe you've done some other languages where somewhere it's a library, and rather instantiating the library directly to tell you, oh yeah, extender library is the way you get our functionality. That's how you get in, right? So you for example, in Java, if you want to use, like Java test, right? You might or JUnit, you might extend some things, right? And so it's kind of a similar modality. So inheritance is another, tool available to us. And like I said, we've been using it, not thinking about it when we do things like extending module, extending bundle. Cool. Questions? Yes. Oh, very good question. So if I'm building an embedded domain-specific language, in other words, building a DSL inside an existing language, perhaps for hardware, uh, do I have to use inheritance? How common is that? Extremely common, as you surmised, right? It's a very convenient way for you to encapsulate your functionality for the user, right? And so um, I can't, of course, make a broad statement across all embedded DSLs for hardware, but yeah, a lot of them are definitely going to take advantage of inheritance, and you're going to extend certain classes to do your functionality. Typically, it's a very common pattern. It's a very convenient way to kind of incorporate someone else's code into your code, right? Like I said, and when you inherit from module, right, there's a lot of things for it. It, gets you into the scope of, when you inside your module actually declare, let's say, a val to uint, that thing registers itself within the module that's surrounding builder context, right? And so by extending module, you've now created that builder context It'll track things like it'll add things like clock and reset to your IOs and that kind of stuff. Cool. Okay, so let's try it out in Chisel. So here's an abstract class, which we're going to say, you know what, we're going to build up a library of operators. In this case, it's a unary operator, right? So it's, some number of bits. The operation is abstract. It takes a uint in, uint out. We have IO on this, sure. We have, the thing coming in, the thing going out. And then we apply the operator to whatever we send in. So what's neat about this is we can go ahead and now that it's abstract class, make concrete classes, and by changing that operator, we can change what it does. So for example, if we want to just pass through and do nothing, great, pass through and do nothing. If we want to make it negate, great, negate. So as you can see in this case, we're extending this abstract class, we're passing with parameters through, and we happen to be defining concrete operators when before it was abstract, but the rest of the class we're reusing, right? So all this IO and connections we're reusing, which is non-trivial, right? If you think about a lot of hardware designs, a fair amount of time is spent declaring interfaces and connecting them. So to be able to reuse that is pretty cool. Questions, concerns? Okay, so let's get more ambitious. Okay, let's say, for example, instead of doing a unary operator, I want to do a binary operator, right? In this case, I want to apply an operation to A and B, two different operators, two operands, get a result C. And on top of that, I want to make it decoupled, right? I want to have a notion that, the inputs may or may not be available, the output's going to convey that, the output may not be ready to be consumed. And so in other words, this operation is only going to be done when both inputs fire, but in other words, they're both ready and valid. And we'll actually, to make this more scalable, we'll go ahead and buffer the results in the register. So in other words, it goes through to get two inputs coming in, and we'll put it into this buffer in between. So here's some functionality, right? This may give you some vibes from last Wednesday about how we built our queue, right? We had the full bit to kind of track out as full. But the key thing to note is we have an abstract, method like we saw before, but it wrote a pretty legitimate class around it, right? This is a real module. And now we have this busywork set up. We can now go ahead and instantiate things like add and subtract really simply. And they get all these benefits of decoupling and the buffering, right? Imagine if you didn't have that, right? And you said you had to have all of the code in the prior slide, copied twice, right? All of it here for this one, all of it here for that one. If you copy and pasting, if you're trying to still copy and pasting in your programming, that should be a red flag. There's a chance to get reuse and refactor things, right? And so here we've done that, right? These are two different decoupled operators, and we've pulled out the common functionality into this abstract parent class. And then just, to even do more object stuff, we're using a companion object where we can literally just give you one of these right classes based on a string. So, give me a plus, I'll give you a plus. Give me a minus, I'll give you a subtract, right? So this is pretty neat, right? So as a result, the user can just say, hey, I want, just a coupled thing for an add, right? That's really concise syntax for them. Writing another operator is trivial, right? Another operator, okay, yeah, define the operator. If you want to use the factory method, sure, add another line to the factory method. But you get all this stuff, right? I mean, you can appreciate that, there's a non-trivial amount of Verilog code down here, because that's what's required to support this. I, of course, could also do a trivial test execution where I, every other cycle I put some inputs. Okay, so 0 plus 1 is 1. Then it's going to be 2 plus 3 is going to be 5, etc. But yeah, we're using things we've been covering, right? We have our abstract class to share functionality. In this case, we're also using a companion object to, ease declarations. So they can just say something like, hey, give me an operator, and then we'll give them the right operator. Here's even the pattern matching we covered, earlier in the week being applied. Cool. Questions? Yes. Okay, so is this kind of like operator overloading in the sense that op has different behaviors in different child classes. Is that what you're asking? Yeah, so I don't know if overload's quite the right word. Maybe I guess technically in Scala we just find it's not override. It's just we're defining it, right? That op was originally a abstract method, and so we have many different concrete versions of it. And that's kind of the whole point of inheritance is now we can mix and match things, right? We can have the shared code base in the abstract class, and then if we want to have different things for each instance, we can have this thing. So you're right. So op, what does op do? It depends on the concrete class. But that's the point, is right? These things are largely the same, right? These decoupled operators are all going to need, to have these decoupled interfaces, have the buffer, the full bit, the tracking, the ready valid signaling, all this logic. Let's write that once and reuse it, right? So you may find opportunities for this in your projects where, you want to have different classes, they do different things, but you see a chance to get reuse. One way to do that in reuse is with inheritance. Cool. Okay. So yeah, we fired this thing up. Seemed to do okay. So now the final class thing we're going to cover in this class, puns intended, Scala trait. Okay, so we said that abstract classes or classes in general you can inherit. You only can inherit from a single class. And so I mentioned how the reason why they did this in Scala is known challenge of having multiple inheritance, and that is if you have multiple inheritance, sometimes it can be ambiguous where things come from. So one instance of that is what they call a diamond problem. Where let's say you have a parent class A, two children classes B1, B2, and then they both inherit from A. And then you have a final third class C, which inherits from B1 and B2. And then, B1 and B2 may both override a method from parent class A. Which one do you take? Right? And so it's like these kinds of challenges, right? And so as a result, Scala's like, no, trust us. You don't need multiple inheritance. You'll be just happy with single inheritance. However, if you feel the need to get some functionality from multiple sources, you can do a trait. So what does that mean? So you can have multiple traits inherited, but it has some constraints on it. And so those constraints make it easier to work with this, right? That's kind of the point. So there's so many different subtle variations of the class in Scala because you have certain trade-offs. There's certain things they enable, certain things they disallow in terms of functionality. And if you use them correctly, you get nice properties, right? You can imagine someone could have just said, you know what? Forget all this stuff. You can have only class and then, functionally you still write code. It's just going to be more verbose, more clumsy. Why not? And so in this case, Scala chose that with more features. We're having more features, you got to learn them and separate them. But if we use them correctly, life is better. So what do we get for trait? Number one, you can inherit from multiple traits. One of the main, catches for a trait, it cannot take constructor parameters, right? It's literally just some things you're bringing in, but that's it. And so sometimes here is referred to as a mix-in, because that's kind of the idea. Is you aren't fully inheriting everything. You aren't just copying something. It's kind of like, think of inheritance normally as, I'm inheriting from this. I'm basically that, except, whatever you change about yourself, the overrides. Versus a trait is more like, this is this trait. Okay, let's take some of that and mix it in, right? It's not like you're fully a copy of that thing. And so as a result, you can have multiple traits. It's just fine. And so we use this often in Chisel to add a little bit of functionality to types of modules. And so you're not so much exact clones of this original thing. You just want a little functionality, right? So let's say, for example, you want to have a library to help you do some development and especially debugging via printing. Let's say your printf for life, right? And so how might you embrace that further? Let's say you built this trait, print and sim, which is going to toggle the ability to print from a certain component, right? So what's interesting is here's a regular, module we're doing. So, extends module like normal, single inheritance. But then we're going to go ahead and mix in this trait. As a result, these things are kind of injected into this class, right? They're mixed in. And so uh, doesn't seem like much, but for example, we added in this IO. So now the test case driver can actually access this port. So notice how, if you look at the class here, this module normally only has an output. Um, However, thanks to this mixin via a trait, we now have an input, right? So remember I said earlier, saw sometimes with object-oriented inheritance, you can complicate readability. Here's that example, right? Where, in no place in this code do you see print enable defined or even used, but because of the trait being mixed in, that's now actually part of this module, right? So if you structure your classes well, perhaps people won't need to think about this much of the time, right? It'll be more clear if you only think about counting, you only think about counting. However, if they want to think about other stuff, they can look at other stuff via this trait. And so there's a little bit of human judgment here about how you encapsulate things in which ways, but you can still see it, right? So okay, this thing's going to work. If we have the print enable on, or in this case off, we won't see it, but if we turn it on, we can see it. And so the kind of proof this is actually running, yeah, that's the one actually running 3 steps, right? So you see, we can turn this counter on or off. And this print string is coming, of course, from this when, the actual message we left abstract, and they're actually giving concrete value here. So other than this message, you wouldn't know there's anything being done to this module other than this inheritance. And so like I said, when you're using this kind of mix-in stuff or just inheritance in general, think about what kinds of things people should be thinking about when they're reading your code, and will be more intuitive, right? There's some human judgment there. Cool. Questions, comments? Yeah. What wouldn't work? Oh, if I don't bother defining message, what happens? Yeah, you get that concern. Now, as let's talk for a second as a library designer. It's actually probably the right behavior, right? We actually probably want people to be forced to override this, right? Now, alternatively, we could say default, right? And that might work, but it may not be what we want, right? That's not very helpful. So I think, you could also say change me, right? And maybe make it more clear to people. They're supposed to override that, right? So like I said, think about your users. As we were talking about before lecture, your users are not going to read documentation even if you write it. So number one, write documentation. But number two, understand your users are not going to read it all. And so then how do you structure your classes such that people that are not only not having read all of your documentation, they haven't even read all of your code, how they can be least surprised in the least amount of time. This is one of the things we're talking about. Yeah. Like an empty string, I believe it might just keep printing lines. Because we are calling print lines, that's what's providing the new line. Um, but yeah, like I said, so picking defaults to help you guide users, right? Change me with, def message string equals in your class, right? Then if you're like, why am I not getting the right printf from your debugging tool? And it's like, oh, look, you should have changed that, right? So, like I said, think of ways to make it clear what's going on. Cool. Okay, so between today as well as prior lectures, you see me explain not one, not two, but 5 different class mechanisms inside Scala. And so I made this slide to try to recap what's going on, right? So, oh my gosh, how do I manage all this complexity? Well, let's just cover more quickly. Even though there's 5 of them, over time, you'll drink the Kool-Aid, you'll get used to them, you'll embrace them. Okay, so first one, class. It's a regular class, right? You define a class with class. We've been doing this all the time. We define modules, bundles. We're used to that. Object, we covered that next in this course, right? That was a singleton object, meaning there's only one for the entire lifetime of your program. And so we saw a few different use cases for that. One use case was having a companion object, meaning there's an object associated with a certain class. And so that way you can get things like multiple constructors using the factory method approach. The factory pattern, that was totally fine. Other times, which is underappreciated, you just have constants or functions that don't take any state. They're just, a pure function. And you just want to put them somewhere in the code. And guess what? You can't just have functions floating around inside Scala files and even inside classes or objects. If they really aren't associated with a class instance, put them in an object, right? You can have, my params or whatever it needs to be. So an object is a great way to kind of group together things. Or maybe you have your own library, your own util library of, functions you like to do. Put those in a util object, right? That way you can have call those functions anywhere you want. The other one, of course, is a case class, which is like a class. It has some restrictions and gives you some things for free. And so that's why you kind of do it. So it doesn't have the full flexibility in terms of, inheritance and a lot of other stuff, but what you get things like a really nice toString method. So it's handy for, printing debugging. You also get pattern matching, as you saw earlier in the week. So you can quickly grab fields out of stuff. Has the ability to do copies really easily. There's a lot to like about classes, case classes, I should say. And then today we've covered both abstract class and trait. And these are ways that are useful. These are useful in the context of inheritance, right? Abstract classes are, a common parent class that you can inherit from. And so in Chisel, perhaps you might use that for such sharing functionality across different modules. And then traits are a way to also inherit, but you can now inherit from multiple traits. And so perhaps something not as, full-fledged as a module, but some sort of functionality might be a good use of a trait. Cool. Questions, comments? Okay. So then let's come back to the things I promised earlier about, like, let's say templating types. So you can parameterize a type, meaning the type itself is, a parameter. So Scala, as I mentioned, has this, rich functionality regarding types. It's something called type bounds, where you can basically say, hey, I want a type. It's not just any type, but a type that conforms to certain rules or certain parents or whatever. Interestingly, when you start templating types in Scala, at least I ran this problem a lot, but maybe everyone else is different. You get this error message from the compiler that's kind of baffling, and it mentions something called type erasure. And you fall down a rabbit hole, and you find out that there's kind of like this original sin that's kind of been propagated for years, where based on the way Scala chose to implement generics in the actual JVM bytecode, certain choices were made. And the choices were made because of the way Java implemented generics. So the original version of Java did not have generics. That was added in by a later version of Java, I believe approximately Java 6 or something, but it was not part of the original Java. And because they kind of grafted generics into the JVM bytecode in a way that was supposed to be backwards compatible, there were certain shortcomings in the way it was done. In particular, it didn't record the types in the way you would like the types recorded. So as a result, Scala, built on top of all those layers. If you have generic things in Scala, sometimes you lose the type that you're templated on. That's annoying. If you find that annoying, you can follow this blog post link, and you can learn how to add another import if we get down towards the bottom of this. And the other import will basically tell, here we go, Scala to add additional state to your program to not lose track of that type. And so, yeah, I found this kind of very annoying, very unintuitive as a programmer. And then, like I said, it was an original sin that was kind of like, amusing, because I found out that the primary Scala creator, Martin Odersky, was formerly on the Java team and created generics for Java. So he was extremely unfamiliar with this problem, and so he kind of propagated through. But like I said, I'm in the attitude of, make things not surprising. I would have probably included the type tags by default in the language, and if people are worried that type tags are too much performance penalty, they can import them and turn them off, make it go faster. But that'll be on them. But that'd just be me. Anyways, let's see how we actually do it. Here's a Chisel module, and we're going to have a type parameter. That's what this square brackets are. In this case, it's saying we want something, a type T, which, is unspecified. It's a parameter that inherits from Chisel data. Okay, so in other words, this thing's a pass-through, so we can, simply pass things through. We can change the type really easily, no problem at all. Right, any of these types are possible. It just goes through. So from our point of view, rather than worry about all the punctuation, we can just basically, typically, copy-paste this, and then boom, now you have, that means you're taking in a template type, and then you actually pass the type in here, right? So, or so not the type, but the generator for that type, I should say. So notice how, for example, I could have, if I was being more verbose, I could have done this, right? But I didn't have to because it did type inference, right? It recognized, oh wait, I passed type in here. That must be a type I meant to pass in here as well. So it inferred that on its own. So for the most part, you don't need to do that. But you've seen me a few times in this course do things like, I want, okay, I want a seek of, 1, 2, and 3. Guess what? That's a seek of int, right? That is the seek is a generic collection, int is the type. But if I want an empty seek, nothing is the type. It's actually like the base type, right? Because there's no type given. But let's say I want an empty type, but it's going to be int eventually someday. You can do that, right? And notice how we talked about earlier today, it's actually giving me lists, right? Even though I keep saying seek, it's giving me a list. Cool. Other questions or comments? Yes. Yes. So I'll do that slide in a second. We can make that a parameter in 2 seconds. Cool. Other questions? We can appreciate another type hierarchy. Here is the chisel type hierarchy. It's actually the older chisel type hierarchy. If you go to the homepage now, you'll see a slightly different one because guess what? The language is changing. They're rearranging the type hierarchy, but this is, a couple years old. But it kind of comes together, right? When it comes to actual data carrying components in Chisel, data is a pretty safe base class to work from. We often spend a lot of time working on uints or bool. Bool, is like a one-bit uint in many ways. You can see a uint and nested are both kind of siblings in a way, both inheriting from bits as well as nums. And you can see how they see in this color code, right? That a lot of these other things are things most Chisel developers don't see because these are internals to Chisel. We say things I want a uint or whatever. But here we are building more sophisticated generators. Perhaps it's one of those times when you're going to say something like, yeah, I know I want something to send from data. Or maybe you don't want data, because data also includes things like Beck. Maybe you really want to tell people, you know what, I want something that sends, from bits or something like that. And you could be more restrictive. Okay, so then following up, here's our queue. We're going to say we're taking in a template parameter. Then we need to pass in the template type as well. Otherwise, this is mostly the same code. Here's our model. And go ahead and run it. And yeah, you can see how we're able to give it the generator, right? And so we aren't forced to say, my queue over here, right, so to speak, because it's doing the type inference. But yeah, now our queue, version 7, took us a lot of tries. Pretty spiffy, right? It's able to do the things we hoped, right? It's parameterized in depth, any number of depth, power 2, not power 2. Bits don't move any more than they need to. Can do pipe if you want. It's a choice, right? The actual type it takes is parameterized. It could be a uint, it could be sint, whatever you want, a bundle, no problem. So this is pretty flexible, right? And so I like showing this case study because that's real design, right? You can draw things on paper that are really flexible, but it's easier when you actually incrementally keep tweaking and modifying to actually see what you need. Like I said, occasionally when you're writing something, you're going to need it for the next thing you want to tweak. Rather than writing it right away, write that down somewhere, and then probably sort of those features you haven't built yet, which one you think is most impactful, and do that one next. Take these kind of incremental baby steps the whole way through the development process. Cool. Yeah, so we have our templated queue. So any more questions on inheritance or templating? Yes. Ooh, good question. So if I have an enum, what does that qualify as? So enums, I believe, under the hood map down to uint. So that would technically qualify as data. But now you have piqued my interest. Let's go find out. Yeah, okay. So, oops. If we were to say, hey, class, my enum extends chisel enum, which now we understand this works via inheritance, right? val, we can just be simple, A and B. Is that okay? Yeah, we're so far so good. Now, if I was to say, we need generators, so maybe I say, let's see if I just say my enum, what happens? I might need to say new my enum, because normally they're ones we're using an object. Okay, so this is not obviously compiling. I'm not positive this should work, but we were trying anyways. Um, so you can see the error game of the compiler is basically it's checking that, is my type bounded by, in other words, so it's satisfied its constraint. Uh, the reason why there's a symbol here, there's actually different types of constraints. You can say things that are at least a parent of or a child of or et cetera. There's contravariant, covariant types, this whole thing. Um, and so, yeah, I'm not sure I can get enum to match this, but maybe we can. We can look into this after offline. Cool. Interesting question. Other questions? Although, I guess we pause for a second and think about that. So in enum, I'm just trying to think of it like conceptually matches that what we think of as a type, right? Because like an enum is less about being a type and more about being a concrete value, right? We like assigned enums, you compare against enums, you can pattern match against enums even. Um, so maybe it's not quite a type in the sense that we think of what types are. But yeah, still a good question though. Um, okay, then once again, coming back to the project, like I said, the whole point of the project is you guys experience not just building chisel, but also um, the whole project experience of having an idea, coding it up. Of course, despite best intentions, there's some challenges and hindrances along the way. Overcoming those things, seeing what the final result looks like. That's a good experience to have. So people think about the projects, come to office hours, come talk to me, or on your own talking to potential partners. Start off by looking at what applications or domains you're most excited about, right? If you're interested in that area, or already have a background in that area, this will make it much easier for you to like jump into that space, right? But even if you don't have a background in the area, if you're just interested in it, that's cool. Um, Other things to think about are, so for this course, we're excited about hardware generators and reuse. So think about, does this thing have opportunities for parameterization or some sort of flexible generation, right? If it's something where it's like a very concrete protocol with only one possible implementation that could ever possibly be needed, that's not as exciting for this course. It doesn't mean it's a no-go, but it's like, maybe not as exciting. Come talk to me about how to maybe make it more flexible. Um, Another thing I like to have is projects that have room to accommodate students to have different amounts of progress, right? Like I would be really sad to have a project where it's like you put in work for 5 weeks, the final thing didn't work, and you have nothing, right? It's kind of more of a waterfall style design, and we're trying to avoid that. We want to have this more agile, iterative approach. You want to approach it working in a week or two, and then keep making it better. So that way, depending how far you're able to get, you still have something that's there and something that works, right? So, um, in terms of what this means for picking a project, occasionally there's a project idea people have where it's like the minimum viable thing is still pretty big, right? In which case they can never even finish the first version. If that's the case, that might be too big of a project. Think about how big and complicated it is and make sure it's not too gigantic. Um, Another thing to consider is what's been done in this project previously, right? Chisel's been around for a while. This course has been around for a while, right? So it's because someone's done insert your keyword and chisel before insert your keyword in some other language doesn't mean you can't do it. It doesn't have to be completely novel, right? This is a course project. But definitely look at how they did things. Look for things you might do differently, things you might do better. How would you differentiate yourself? It's okay to kind of repeat if you find some way to be a little different. And then also consider how you get started, right? What do you do? What's the most simple thing you can build? How would you test it? How would you know it's even right? How would you even build your first test case even if you know your first test case is right? Maybe you can find code in some like Python that does the same functionality, so you can compare the numeric results from the beginning to kind of know you're on the right track. And also start developing and think about, what functionalities can you defer to later on to get that least simple thing to get running to close the loop the first time. Okay. Then I did want to highlight some cool student projects in the last three offerings. It's the fourth offering of this course. This is by no means exhaustive. It's some ones I think are kind of fun to give some flavor for things. In the first few offerings of this course, we had a lot of students doing ciphers and hashes, and the reason why is our homework should be based on a lot of ciphers and hashes, since I've changed curriculum since then, and so correspondingly, the number of hashes in projects has also gone down. But some of the most, sophisticated leading edge hashes are algebraic and whatever stuff, and they're pretty cool. So there's some fun stuff there to use some cool parameterization. People have done things like give me a neural net topology and I'll just turn that into straight hardware, right? So you can imagine how taking some sort of representation of a neural net, it does the math on bit widths, actually connects the things together and does that as a generator. That's pretty cool. We've had people doing things like TPU, like actually having to install matrix multiplication across different blocks, shipping blocks around, things like Bloom filters. The Mandelbrot fractal is kind of fun. My point to Sally has said, even though we're making hardware generators, it's okay to have, for this course, a hardware generator that kind of depends on a testing harness. In the case of the fractal, like there was not really a plan for how the hardware would be self-standing and have like the hardware visualize the fractal. No, the hardware was plugged in a tester, and a tester was able to actually visualize the fractal for you. But that's okay. This is a class. Have fun. Smith-Waterman's a genome sequence alignment algorithm. Very amenable to parameterization. You can change the size of your array and how much you're matching, that kind of stuff. Really great opportunities for flexibility in generators. We've had an image histogram equalization last quarter. There was someone taking video frames and applying a filter to them. So you see a lot of these projects kind of have similar vibes to them, right? They're something where it's not a whole on, giant system. It's kind of a more modest system, but also like there's room to have parameters and flexibility in generation. That's what's most exciting, right? You have something where you have some knobs to turn, and not just changing numerically the size of something, but actually changes the internal structure in some interesting, fun way. Like I said, if you're kind of still stumped, come talk to me in office hours. I have some ideas of things that, I've been pitching people might do. And do try to find a partner. We're really, because the course is so big, we can't have too many individual projects. Cool. Any project questions or other questions? Okay, well then that's all, folks.